thank Professor May and others who were part of inviting me here. It's nice. It's sort of a new group of people for me to meet. So if you don't know my background too much, so I have mainly been working in symmetric crypto. So well, maybe 2 years ago or something, I had a PhD student starting working on actually LPN, and then we got interested and did some work in this area. So we had one paper at ECRYPT where we used coding techniques for improving algorithms for solving LPN. And then this work that I will talk about here was sort of a continuation work of this, where we say use the ideas but introduce a few new sort of key components to make it work. And we also did some additional work on ring LPN, which will appear in IEEE transactions, information theory. So yeah, and Martin said that I would say something about the state of the art. We all got a very, very good introduction to, I would say, some of the key components of these algorithms for solving LWE. And as you also saw on Martin's slides at the end, so the most recent works was this paper being presented at Crypto, and there was also Kirchner-Fouquet at the same conference, and I would say that the algorithms are quite similar, and with a few differences. This other paper, Kirchner-Fouquet, they also have some quite impressive results, and when it comes to numerical values, I think they are a bit displaying numbers which are a bit better than in our work. And in particular, they also have some implementation, so they managed to well, solve a certain instance of the 0-1 LWE problem, which I found very impressive. So much faster than what was expected before. So that's a bit on the current work and what we have. So I only have the slides from our crypto talk, so I will use them. And it's my student Shen Gu who have done the slides, so should credit him for that. You already know a lot about these things, so but there will be a short introduction again, so you can maybe just check that you have the knowledge of everything from the previous talk, and then I will talk a bit about the new ideas that we introduce, and then come to some results in numerical values and some simulations and so forth to show how it's done. So again, coming back to learning with errors. So as you already heard, we have quite many parameters to play around with. So this was the definition of the problem. So we have this secret vector S, and we can get samples of this form. So the oracle randomly picks some vector R and then we get this product, and then there is an error added to this value, and the error follows some special distribution. So and the binary LWE is, as we already heard, it's when the secret is small. In this case we say it's in this alphabet 0, 1, but you can of course think of other cases where you have the secret not being randomly chosen but from some smaller alphabet. So and yeah, so we have two different problems we can look at. We can look at the decision problem, just trying to distinguish these kind of samples from truly random samples, or we can look at the search problem, so where we actually try to find the value of this secret vector S. So and in this work and this presentation we mainly focus on trying to find the secret vector. The distribution then is as typical the discrete Gaussian with some standard deviation of this form. And okay, so we know that LWE is very important. As I said, it can be seen as a generalization of the classic LPN problem. And we have many different cryptographic primitives constructed from LWE. So maybe fully homomorphic encryption is the most exciting one currently. And it has this nice property that, it's in the quantum, post-quantum world. So even if we have a quantum computer, we don't know at the moment if this problem can be solved in opposite to factoring and discrete log. So it's a really important and maybe the kind of future cryptographic assumption. So it's very reasonable to look at this problem. So what about looking at the complexity of solving LWE? Well, quite many papers, they focus on looking at the algorithmic, the asymptotic complexity. So we have a lot of results on like the complexity being of a certain form. In this work, we don't focus on asymptotics. So actually, we try to be more practical. So we look at more practical security in the sense that we try to actually find the explicit number of operations that we need in order to solve a certain instance of the problem. So that was the way we looked at this. Then of course we can also look at the asymptotics of algorithms, but we didn't do that yet regarding this work.
You don't limit the number of samples, right? So it's
not more than the complexity.
Yeah. Okay.
So yeah, it's not so obvious, because I have received many papers where people use many more samples than their claimed complexity. So it's it's. So then, coming back to the different types of solving algorithms, also we heard this before, there are the possibility of using different algorithms related to lattice problems, so lattice reduction. So that's one set of possible ways to try to solve the problem. The good thing is that you don't need so many samples for these algorithms. The bad thing is that it's a bit difficult to estimate the actual practical complexity. So how many operations do you actually need for these algorithms? So there is another way of doing well, another type of algorithm which works very well asymptotically, but is not very practical. So, and the third type that we look at here and we heard before is the BKW type of algorithms. So it requires many samples in general, so that's maybe the drawback. You need really a lot of samples. On the other hand, this is the best type of algorithm in order to actually give some fairly accurate estimates of what you're actually going to get in complexity. So we can because it's a combinatorial algorithm, so we can determine the complexity in a different way from these algorithms and be pretty sure that we will end up with such a performance as we get. So this you saw before, the BKW algorithm. So it was originally for LPN, and for LPN it has this sub-exponential complexity, whereas for LWE it's in general fully exponential. And here is maybe less nice introduction than what you saw with Martin. So you have all these different R vectors. So we have a sample, and in each sample there is an R vector. So now you take your R vector, you split it up in a number of different parts, and you treat one part at each time. So this is the number of positions in one part of the vector, and then you merge and sort according to the value in this part. So you look on these, well, entries in the vector R, and you find, so for example here, so you have, this is the part you're currently looking at. So you have two samples with the same part here. Then you, in this case, you subtract, or if you have the opposite signs, you would add in such a way that you cancel out this part. And what is happening is that the noise is slightly increasing. But you get rid of some contribution. So basically you get rid of a few entries in the S vector. So you can now cancel out some of the entries in the S vector, and then you continue and repeat this many times. And every time you do this, the noise will increase. So you get 2 times the number of noise vectors here in the final noise, and you just repeat it. So that's the classic BKW. And yeah, so here is some kind of collection of different contributions. So there are, so if this is the BKW paper, so there are some work in the line of LPN, and then others in the line of LWE. And so some contributions when it comes to LPN is the use of a fast-Schwarzschild transform. There was an observation that the secret, so the distribution of the secret, if it starts with a uniform, then it's by a simple transformation you can have the secret to be distributed the same as the noise. And then we introduced this idea of using codes in order to slightly increase the performance of these LPN algorithms. And for LWE we had also here some of the more important things, contributions. So for example, just the application of this algorithm to LWE. There has previously been an observation also here that you can just transform the secret error to the having the distribution of the noise. There was the lazy modular switching technique that you saw, which is, well, at that moment was the best BKW type of solver, and there was at ECRYPT the addition of using fast Fourier transform to slightly improve this LWE solver. So that's sort of a background on some important contributions in this area. And okay, so the algorithm we are going to present is using codes in some way. So we need some background from lattice codes. So we use lattice codes as a tool to be able to estimate the noise, the performance, and so forth. So we just need some concepts of lattice codes. So we have lattices, and if we have a query code, we can construct a lattice from lattice codes. This is known as construction A. So we pick a query linear code, say C, and then we construct a lattice in this way. So points are everything that is congruent to a code word modulo Q. So this is over FQ. So we are going to use just query linear codes, but this seemed to be a good framework to do the analysis to construct the lattice codes, because we know some things about the performance of this construction A. So that's why we introduce this. So so this is trying to a bit answer this. And so the idea of why we are using lattice codes in the sequel here compared to what we saw before, this lazy modular switching, is that we can have a kind of better shaping, which will give us a better performance. So actually this lazy modulus switching can be we can think of it as some kind of lattice code also, but from these kind of codes we can have some slightly stronger performance. So we have to introduce a second moment of the lattice. So it's defined as well, like this. So it's the second moment per dimension. So we divide by m here. So and it looks over this Voronoi region. So all the points which are closest to a point in the lattice. So this is some things we need from lattice code. So now let's try to explain the new ideas. So it's a BKW type of algorithm. What we do is that we split in many different parts. So actually you say that the new part is like these things here. So this line here, this corresponds to the vector r. So these are all the positions in R. So we are going to try to cancel out parts of this vector R. So, and we do it in different steps. So, well, first there is a initial step, which is just a Gaussian elimination step, which transforms the secret S to follow the noise distribution. So we just make a simple step so that S is now distributed according to the noise, which means that S is also small. So then we start, so we put here a number of BKW, classical BKW steps. So, and we could basically skip this part and have only this coded, but it's so when you start, it might be that the noise that we can introduce, you will see in the next step, will be so small that we cannot have anything else. So we could only have trivial codes, and then this corresponds just to classical BKW. So that's why, just to highlight that we could possibly start with a number of classical BKW steps. So that's this first part, so there is nothing new here. But then we have the new part here, which is cancelling a number of positions based on coded BKW reductions. And I will explain what this part means in a moment. So then we have cancelled all the positions up here. Then we have some final positions remaining, and so there is here, the next step here is is to do a partial guessing. So this part here, then we guess, well, this is also a guessing step, but this uses a fast Fourier transform. So in this way we run through a number of different samples, and we also run through a number of different possible values for this part of the S vector. So this is following, say, previous work, the idea in using fast Fourier transform. So you can basically with a good complexity run through many samples and many different values of the S vector here in one step. And the final part up here is just a guessing part. So we added this part so you could choose also to guess a few values up in the top. It could be beneficial, in particular if you, for example, have a 0-1 case, then guessing a number of positions here might not cost so much. So it could be that it would be beneficial, but it gives sort of a maximum freedom here. So it could be that you are not actually guessing anything and just running these parts. So this is the structure of the algorithm that we proposed. So we have to look at the different steps here.
Thomas, may I ask a question?
Yes.
So, you said you focus on practical parameters, and I kind of see that all these things make sense in a practical way to optimize your running time maybe. But from an asymptotical point of view, which of the colored parts make a difference? Is it only the blue part that makes a difference? Or at all?
Yeah, from an asymptotic point of view, I would say it's only
I think so too.
only this point.
For the others?
So this is basically to gain some constant factor by.
Basically, it's a search to decision. It's basically just a search to decision reduction done more efficiently.
Well, but this is search, right?
Yeah. But if you do a decision problem, that this is not even there, so it's
that's true. That's true. Yeah.
And since the search decision is
It's polynomial, so it doesn't make a difference. Yeah, that's true. Yeah, that's good explanation.
Yeah. So this is sort of the overview of the algorithm, and then.
But the right part would be
Yeah, so this is essentially where we have, so this is the main contribution, and then we also had a slightly different fast Fourier transform part in this part 5 here, so which is also a contribution here. So this is then trying to explain the idea of this coded BKW. So again, we look at this. Well, we have a sample, and we have this R vector, and so we introduce here a notation. So Ri here, this is the vector R only in the index interval specified by I. So this is just one block. So we are looking at the R vector in this particular block that we are considering. So, and the idea is that when we look at this block, so we pick a code. So the code has this dimension, but this length. And when we use different blocks, we use different codes. So, and this is, also comes back to what was discussed by Martin, that the noise contribution from different blocks will increase differently. So in order to get the smallest contribution to the noise, so the first blocks, the noise will double many times, whereas for the last blocks it will only double 1 or 2 times or so. So we have different lengths here, so that the noise contribution from different positions will all be roughly equal. So we pick such a code, and the idea now is that when we have this kind of we have a sample with this R. So we look at this product S times R, and if we now look at this R vector as being a code word plus some noise, so then we can write in this way. And if we now find, so this is sort of the basic idea of what we did before with LPM, that we then try to run through the different values of this code. But now for LWE we need many steps, and we need to use this in every step, so we need something different. And so what we do is that we run through all samples, write them in this way, so we map every vector here to the closest code word in the code, and then we get the noise. And then we sort them, so we put them in different partitions or buckets. So all samples going to one particular code word here, they are put in the same bucket. So then we have say the dimension is b, so we have q to the b different buckets, and in each bucket there will be maybe a few samples where this R vector is mapped to this particular code word representing this bucket. So then we can add or subtract, well, if we take them from the same bucket, you would subtract two such samples. So by subtracting two such samples, you will cancel this part, and the remaining part will be two such terms, S times E. But since S is small, because we transferred S to be a small value, and E is also small, so then the value here will be small. So in this way we have cancelled out the contribution except for some small, which we call error noise. So, so what is the advantage compared to standard BKW? Well, you can have the length to be longer than the dimension. So BKW is just having a BB code. That's BKW. But here, so by choosing a longer code, we can cancel more positions in one step than standard BKW. The price we have to pay is that we get this additional noise. So the problem is that we need to control this noise in some way. We need to see that this noise will not grow and be too large.
Thomas, how do you do the decoding to CL?
Yeah, good question. So in the small examples that we have been running on the computer, then they have been small. So then we do just syndrome decoding. So just a table and just a lookup. So it's in that sense very, very quick. In some of the figures we have given for different parameter choices, we also just refer to syndrome decoding, because then the complexity is so large that we can afford to have really large tables.
I'm not exactly sure to understand the strategy. So here you're using the code inside each block, right?
Yes.
Okay. So in this case, BKW wouldn't be the code of size n, but the code of size 2n, the complete code basically?
So if you have...
It's a BKW is complete code.
Yes, okay.
This is the dimension, not the
Oh.
So you have one block. In BKW you would have B positions, and you will cancel them out.
Yes.
But if you have another code which has a length which is more than B, so then you will cancel out a few more positions.
It's just misunderstood the notation. So it's the code of size 2b, which is equal to big N.
Q to the B.
Okay.
Yeah, so Q to the B is the dimension of the code, and the length is longer. So that's the idea of cancelling out more positions, but introducing an additional noise term. That's the problem. So okay, so basically we can, if we do these steps over all blocks. So when you do the first block, you introduce well, the sum of two such positions. And then when you do the next block, then the first block will add another noise term. So the first block will add many different noise terms for each time you process in the BKW. So you get a full noise. So it's a bit of a messy formula, but first of all you have all the noise contributions from which are present in the samples. So if you have a BKW with t steps, then you will add up 2 to the t of these noise contributions. But then you have this additional part, so it's like S times some noise. And from the first block you will add quite many noise terms here multiplied by the S. So in the second there will be 2 times less and so forth. So the noise is summing up here in differently for the different blocks. So that's why we would like, so when we look at this sum here, so these are the noise contributions from each block, and they sum up differently depending on if it's the first, the second, and so forth. So the first one has many different such noise terms. So we would like to select the size of these noise terms, and this has to do with the code. So the size of these noise terms should be very small in the beginning because there are many of them summing up. But then when we continue, so for the last block we process, then we only get the noise we get at this last block, and it's not added anymore. So that's why in looking at the total noise, we would like to have these things here to be of equal size. And because they contain different number of noise terms, then we have to set the code in such a way that the size of these is the same. So the noise here should be small in the beginning, and it can be larger and larger. So we get different codes for each step, and this is sort of the key idea of getting improvements, and this was also noted by Kirchner and Fouquet, but in a completely different setting. That this way to do it gives the improvement. So we have, say, what we call a noise tower, and we have to set the different size of the noise coming from the different codes differently. So we say that all these should be of equal size. So we preset a certain value here for the noise, and then we decide a noise for the particular code. So if this is the total, then this times this to the something here, this should be the total noise. So then we have to set the noise here depending on which code we are looking at here. So the codes we use in the beginning, they will have, say, high rate because the noise should be small, and the code we use at the end, they can have lower rate because then we can have a larger noise. So that's how we build these steps. So yeah, so we get then some results on the total noise. So there is a noise. So this is a transformed S vector, and this is the noise we set when we use these codes. So then we get a total noise of this form. So now we are going to try to determine what kind of codes we can use, and then we have to look at what noise do we get, and then here we just use theory of lattice codes. So there is well, the second moment can be written like this, where this is the normalized second moment, and it's known that it's in this interval. This comes from trivial codes, and it's known that you can have equality here for random linear Curie codes. So, and from this normalized second moment for a code, or for a lattice from a code, you can then get the noise level for the code. So this is given here. So you have to select a code such that the noise level is then roughly in this way. And if you sum up, so then we sum up all the lengths. So this is how many positions we can cancel. So we sum up all the steps we do in this coding part, and that will give us how many reductions, how many positions we can cancel. So that's how we use the different codes. So am I using too much time?
You have like 5 minutes.
Good. Okay, so then I will speed up a bit. So the third part, if we go back here, so the third part was just a step here with exhausting samples and also guessing some values. And so maybe I will not say too much about this. So this uses fast Fourier transform. It's a generalization of what was published at ECRYPT-15. So what we do here is that it's not only on B positions as in a standard BKW, but we can actually use one coding step included in this part. So also here we can just add slightly more to cancel out a few more positions than in a standard BKW step that you could run through with a fast Fourier transform. So there is some different approach to this, where we go through Q different fast Fourier transforms instead of a single one, but it doesn't affect complexity too much. So let me maybe say something about the assumptions and the results we had. So first of all, we have made a number of assumptions in the analysis. So one of them is that the noise variable, so when we add, so we get this noise from the different from the different blocks. So we get the noise all the time, and we add it together. And we assume that when we add these noise terms together, we get a discrete Gaussian. So it's maybe intuitively okay, but not exactly. But still, I mean, we did some experiments and checked that this is reasonable. So the second assumption that we also use is in the theory of lattice codes. So when we look at lattice codes, so actually the series is in the continuous case, but in this case the noise will be integer values, so it's not exactly the same. So there is one deviation here that the noise is uniform over the integer points instead of continuously, but we also here we numerically checked and we computed this G value, and well, we could see that it made sense to use these results from lattice codes. There was nothing deviating.
Sorry, what is it the kind of dimension used in the algorithm, so up to 4, or you use bigger dimensions?
Once again.
What kind of dimension of codes did you end up using?
Yeah, okay, yeah. So in simulation, so this is what we simulated. This is like 4, 1. So this is dimension 1, length 4, and Q is 2053. This is just this is simulation values just to check this particular thing. So then I will come to some other results. So yeah, so this is again the algorithm, and then we can go through the different parts and look at the complexity. And then we can have some kind of expression of this form. So you look at, well, there are some assumptions. So we can fail in the coding here. So and there is some part of guessing here. So this is what it costs, and then there are some probabilities here for not being successful. So we have a formula of the expected complexity like this, and yeah, the number of samples given like this, and so forth. And maybe I will not go into the details of the complexity, but maybe I can just show some numerical results. So there are some published parameter choices here, Regev and Lindner-Perkett, and you can see here that well, for some parameter choices we can get good values. So at least we are much better than previous BKW type algorithms. Still, the lattice reduction algorithms perform sometimes much better. So we should also say that so these numbers here, we were quite pessimistic when we put them down. So we used only, if you recall this G factor, we used only the most pessimistic value here, but we could actually have used what we would have for a random linear code, and if we would use that, then we would have much better numbers here. And there were also some other suggested parameter choices in recent papers that suggested for I think 128-bit security that could be sort of broken by this algorithm. Yeah, and I already said that we use this pessimistic value. Another thing that we also used rather pessimistic was this LF1 assumption. So I didn't talk about LF1 and LF2, but this is the way you treat the samples you have in the same bucket. So if you have a number of samples in the same bucket, you know you can combine them to new samples. So in the LF1, then we have the approach of taking only one and add to all the other ones in the bucket. So if you have n in the bucket, you will end up with n minus 1 new samples. But LF2 combines every possible combination of these n samples. So you will get many more samples in combining all of this. So the reason is that why we used LF1? Well, I don't know actually. But generally the reason for using LF1 is that there is more independence. So you can, if you care about the independence between different samples, then it makes sense to use LF1. But it seems like here there are a lot of heuristics anyway, so maybe LF2 is to prefer. But so would we use LF2, it would also give us better results. And I will show something about something more, but yeah, here. So here is a picture of something we simulated. So this is, here is, yeah, this is Q. There is some noise level here, and this is the number of samples that we kept in each step. And here you can see how the different algorithms work. So if you would only run BKW, so yeah, so you would, so with this many samples you can do like two positions at each step in BKW. So this shows how the variance of the noise grows if you just use standard BKW. So you will hit the variance roof somewhere here around 30 or so. But if you use this coded BKW, so then you can see here that we start with the same. We do some standard BKW steps in the beginning, but then we start using first 3-2 codes, and then 4-2, and then 5-2, and 6-2. So first in every step we do 2 at a time, but then after 4 such steps, then we start taking 3 steps at a time, and so forth. And you can see that now the variance grows like this.
Thomas, the variance roof is the old error that you have introduced from the LWEs.
No, this is just the variance of the uniform distribution. So we need to, so in the fast Fourier transform step, we need to distinguish our error distribution from uniform, because if we guess incorrect, then it looks like a uniform. Otherwise, it follows this noise distribution. So we can, this distinguisher will work up to, we come close to this variance. And what you can see here is also this line here. This is when we, in addition to this coded BKW, we also used what is known as unnatural selection. So this is also Martin's and others' invention. So you can in every step you don't combine. Well, you combine all of them, but you don't move all of the samples to the next level, to the next block. But you actually look at the size of the noise, and so you create more possible combinations, but you only move those which are the smallest ones. So then the noise will not increase as much as in the standard case. And if we just use this so in this case we used it only with 4. So we kept only the 1 out of 4 of the best samples. So then you can see that we can gain a bit more actually. So probably if we would use this unnatural selection and have a much more extreme version here, we could achieve much more, I would guess. So the problem is that if you have 1,000 samples in your bin and you should look at any combination, so you have 1 million combinations, this starts adding to complexity. So you have these 1,000 samples. So we need to find a good way of finding the ones that add to be the smallest. And I guess this is a good passing to the next lecture then to talk about this. So we have we are looking into that a bit, and I think this is maybe.
Actually, I've been doing that already.
Okay.
It gives an improvement in the exponent.
So.
Can you say that again?
Yeah, I've been doing that already, and it gives an improvement in the exponent.
Okay, thanks.
Just very tiny, but.
It's good. So so this can probably be a bit better if we use this technique. And this was also used by Kirchner and Fouquet in their papers. Okay, so that's the end. I guess I'm running over time, so.
Have you tried very fancy lattices like the Leech lattice or stuff like this? You want something very spherical, right? For your fundamental domain.
No, well, I can answer the question. We have not. But I mean that it's. I think it's also a question of the best.
The best
codes, lattice codes, yes. And we only focused on this construction A. I don't know if there might be other ways of doing this. So, and there is also, if we want to use large codes, we can maybe use some kind of concatenated codes and have some efficient decoding and things like that.
Do you even need efficient decoding? I mean, you only need to check whether elements decode to the same code word, which is easier, I guess.
But you have to
What?
map them to buckets.
Yeah, you have to make them only to buckets.
But you need to decode to the nearest code word.
You only need to verify, you only need to map to buckets that elements that decode to the same code word maps to the same bucket. So only need to check whether two elements map to the same code word, which ones
Mustn't be the nearest.
yeah.
But it's
years, yeah, but that basically means syndrome decoding if it just kill off.
Yes, yeah. Syndrome decoding is fine.
You don't need to really invert the syndrome anyway, because you only care for whether it has the same syndrome. You don't need to find the code word corresponding to the syndrome.
If you want to formalize the problem instead of focusing on the solution, what's the formal problem to be solved here? So that's the nearest.
Determining whether two elements have decoded the same code word.
Okay.
Which is easier than determining the code word.
Kind of locality sensitive.
Exactly.
Yeah.
Yes, that's nearest neighbor.
Yeah, it's.
But you want to do this on the torus.
Yeah.
Not really.
You do the small Q every direction.
Yeah, but that's sort of, yeah. In the end, yes, but just in the decoding, you would be only careful whether it's in the same order. So
So may I ask one more question? So in the very beginning you said you have some new result about ring LPN. I would
Well, they are not very new.
yeah, okay. So can you say that? Do you get something really better for ring LPN? Because as far as I understand, for all these algorithms, they don't work much better on ring instances.
So this paper is on ring LPN.
Yes.
So there was a proposal Lapin.
Yes.
So they had two instances. So one is an irreducible polynomial and one is a reducible polynomial. And basically so this is about the reducible case.
Okay.
And we can...
you can do some CRT and then...
Yeah.
Okay, fine.
And
When did
something
you do
more.
that?
That's crazy.
I mean,
It's up to you.
What?
why did they shoot themselves in the foot? Reducible polynomials.
Well, I mean, it's an implementation issue, right? Because it's faster in implementation if it works.
Yes,
So
it's faster not to.
It's completely not Q, right? Because you want to use the NTT, so I guess it shows poor factors, but the factor like that it splits is not the problem, because like you would always want it to split completely, because that allows you to do your NTT.
Oh, so it splits mod 2, but not over the integers.
I think so, yeah. And then the question is kind of how sparse are the factors? That's the
This is LPM. It's a binary case.
Yes,
Yeah. Yeah.
No, but when you're splitting the polynomial, you're splitting it mod 2. You're not splitting it. Okay. Oh, okay.
But I mean, if you look at, if I should answer your last question that you promised to ask every speaker.
Yeah. That's my last question.
So I would say this ring LW is very interesting, because I mean, I guess there are some cases which are not. There was one paper at Crypto, so there are some cases that maybe are not so good, but still there seems to be no way to actually have a sufficient gain if you look at the ring case compared to the standard one.
Very good point. Okay, good. So, thank you very much.
Yes, thanks.